Good morning, everyone, and welcome to today's presentation. We're looking at the integrated approach towards reservoir continuity and pressure communication in the nuclear and all-time E6 and E8 reservoir. This is a petrophysical report. Understanding the fact that a reservoir can be laterally extensive or can be truncated as a result of a fault. Nevertheless, there could be a possible fluid migration, that's pressure communication between that reservoir and the next reservoir that just opposed it. With this knowledge, we have to look into this reservoir of interest, the E6 and also the E8. For that information will be provided as we travel down this report. Looking at the workflow, the first thing we'll be looking at basically is project overview, the problem, the business drive, the data availability and quality check. We'll be looking at the initial pressure condition and also fluid informations and petrophysical evaluation, sums and average for building a static and also ultimate recovery volume estimation. The adding area comprised of 5 major blocks, looking at the map by the side, 5 major blocks. Most of these blocks are ENA, Nuke, Otam, Kuro, and Adim fields. These fields are known for numerous operations within the NAG and also the AG, that's non-associated plant and associated gas plant. Now, this is in line with the supply network, domestic supply network. And all these faults, all these blocks are separated by faults. Some are growth faults. Now, this brings, due to the increase in demand in 2003 of 90 million scoff to above 335 million scoff in 2007. The growing demand requires more fields coming into the stream, and that's why the Otam field has been chosen to support this network. Now, the Otam field was discovered in 1975. And like I said, the Otam field is a rollover anticline separated by a growth fault. So the Otam is an hanging wall, while the Nuke is the footwall. Now these two fields are just opposed and are reservoir of interest in the E6 and the E8. Both of them they are just opposed reservoir. Now the Nuke, on the other hand, came up in 1957. For that information we derive. Now, our major challenges, the major problem from the RFT report taking, we realized that in 1990 and in 2007, there've been a pressure depletion noticed. That is a under pressure condition from the hydrostatic levels. And this warrants the need to understand why and where. Now, the objective of our study is to determine the reservoir continuity if truly this Otam field is continuous, span through the nuke, and if not, if truncated, is there pressure communication. These heads are reservoir development manager strategy plan, and also to actually know the actual volume in order to underestimate, nor overestimate, and also to develop technical skills and integrated workflow from the exploration down to the production within a given limited time, understanding business ethics and good team bonds. The petrophysical also will look at the data gathering, tops and base harmonization, and the visual procedures, petrophysical evaluations, and the sums and average. For the data gathering, like I said, the Otam field, which was the hanging wall, which is the hanging wall, has 7 well penetration. And the Kuro with the Otam are just separated by a saddle. Completion has to be the same in that side. But that's not a major focus, which is our focus is the Otam and the Nuke. at this point, understanding that there is a fault and also production in the nuclear before the autumn. So well 1 in the autumn section and well 6 complete suite of log. Luckily for us, gamma ray is found in all the reservoir, majority of them, and also resistivity is also found there, which means we can delineate if there is an hydrocarbon found there first. So with this also in the E8000 also more information were gotten. We have a PDL, production data log, also the RFT pressure data, and no call, but we have good satisfactory log, even though they are limited. Now, QC of the log, now environmental correction was necessary, but normalization was done. Now, normalizing the log help you to properly calibrate them and also get your desired results. Now, these logs were all calibrated from the nuclear and also the autumn section. And also we discovered there is no radioactive sand found in this reservoir of interest as a result of the SP, spontaneous potential, and the neutron density investigation. From the capillary point of view, we get to see that there's no significant washout, which means that our density log is safe for porosity determination since density log reads near Webb-Ball radius. A technical objective is to, as a petrophysicist, is to provide top quarter rock property and fluid field analysis for the integrated model for static and also dynamic. Support the integrated characterization of these two reservoirs, juxtaposed reservoirs, and develop a petrophysical analysis, sound petrophysical analysis for justifying reservoir continuity and pressure communication between the nuclear and the autumn. Our deliverables will be the fluid field, fluid contact, and petrophysical properties. Looking at the initial condition, the hydrostatic condition of this reservoir. Like I said, we have an under pressure situation. The hydrostatic pressure for the EF6000 and EF8000 reveals a under pressure, which is not normal because it's below the water hydrostatic of right now. This is 0.39 and 0.41. Showing that truly as a result of possibly the growth fault and also the production from the neighboring field. Below this, we have the RFT plots, pressure plot revealing the fluid contact of these two fields. Let's go into the fluid contact for more information. Looking at the fluid contact, the well 7 was able to log in hydrocarbon, only one well, and due to the absence of neutron density, we can't really identify the hydrocarbon, but we know there is an hydrocarbon. Comparing that with the nuclear, which has the oil, gas, and water, we get to see that we can't really correlate this. And with the aid of top and base harmonization that was done first with the production geologist and the PP, we had to carry this out, and we had to move a step further and also do an integrated structural framework. And this structural framework reveals that truly these two reservoirs are not in communication, especially with the thickness to throw ratio being less than 1. But nevertheless, moving towards the east, we have a thickness to throw ratio of 1, showing that truly there could be a fluid migration towards the east. And nevertheless, we have further work to be done at that reservoir level. That's the EF6000 and it's just a post reservoir. Moving on to the EF8000, we get to see that we have our contact clearly identified here. And at this point, we could say the line separating that shows the fault. And we could say actually there is a communication at that level. And the contact level is at 9,210 for the autumn field, while That's the gas water contact. Why the oil water contact is 9,196. These two variations tells us that we could have a possible communication at that level. But at first we want to say no because the fluid types are different towards the depth, airspace, and TVD subsea. But with still the aid of the integrated workflow, we're able to visualize this and see that the thickness to throw ratio was 1. And furthermore, we could see the cross-section revealing the contact level, gas, showing that truly possible fluid migration identified. Now, along strike, we could see that through the biofishy information reveals that both the Kuro that is separated by Sadu, the autumn, are having the same depositional biofishy information. Like I said, that's not our focus, but our focus now, this just tells us the position along strike. While this and the deep, we get to see that there is a great difference. Biofishy, now this was more channelized in the autumn section, if we could looking at it properly. And on this side, we have more shelly sand deposition found there. So alongside with the biofishy biostrat information tells us a clear picture that the forams and the forums information, that the paleo and the forums but are not the same. Alongside the eras, which the age of these two reservoirs, the Bolinga era was for the autumn section, while the Languin era was for the Nuke section. This clearly says that this reservoir is not continuous and truly the fault has truncated the autumn reservoir, possibly lower at the lower scale. With this, we're moving on with our petrophysical evaluation input. This is for the dynamic and also static volume determination. And porosity was done first. We had to do hydrocarbon correction, removing the gas effect. And after doing that, we proceeded with this stands as an input for our porosity determination. For permeability, due to the absence of core, we had to use the lithofishy distribution alongside a nearby reservoir having the same lithofishy properties to develop a PROPEM that was used for permeability determination. While water saturation, the Piquet plot and RW was taken for at the water leg, and this was done for the water saturation. The net to gross was done with the heads-up and also resistivity versus visual plot. That's the sensitivity plot. This is the visual result. Like I said, more channels at the autumn sections and shelly sands at the nuclear section. A net to gross result was done with the heads-up and gamma ray was made users comparing the visual of both neutron density and gamma ray. This tells us that truly there is not much difference. This is the input telling us that yes, that's a good porosity, and truly agreeing with the fact that porosity and the shale section is always lesser than the porosity found in the sand section, that's reservoir. This is the result of our permeability and also water saturation, the JOAS and also the Archie. We see them tracking, and the saturation height function that was necessary for that capillary model build. Now, what we had to do was the saturation height functions were modeled, and after that compared with the logged model to see the possible tracking, because the saturation height function is an input for the reservoir engineer and also the production geologist. Our final result reveals a good porosity found across board and good net to gross in the autumn section, and water saturation from the reservoirs that has this information, and permeability shows that truly there's a possibility of fluid migration. But for the hydrocarbon section, we do not have this information due to the absence of neutron and density. The nuclear also, we have information found there. The EF 8000, we have a clear information that there is a production. There is a good porosity, good net to gross, good permeability indicating possible migration, supporting our evaluation. And also the water saturation indicates that there is a good hydrocarbon, quantity hydrocarbon found in the autumn reservoir. In conclusion, the pressure data analysis reveals an under pressure owing to the fact that there have been a production in the nuclear section and also the faults. Separating that, those are the two indications we have to interpret this. And the fluid contact analysis upon distribution in cross-section plot also reveals that there is a possible fluid migration. And the thickness to throw ratio also telling us that is equals to 1, identifying this possibility also. Petrophysical determination, petrophysical analysis, data evaluation was done for static and also ultimate recovery evaluation to really quantify our reservoir. Now, our recommendation is post-saturation log is necessary for the post-production evaluation, and BHP should be taken from the reservoir of interest, which is just a post reservoir, to really just determine if truly there is pressure communication. Interference test can be done also, and production data analysis needs to be carried out to see the possibility of pressure communication. And lastly, fossil analysis is highly required for this purpose also. Thank you very much for your time. Thank you so much, and we've come to the end of this presentation.